Welcome to VLSI Career Craft. Today we are going to discuss on the most important concept, static timing analysis, which is frequently asked in VLSI interviews. And this particular example is mainly based on the concept of clock skew. So let's get started. For the below circuit, flip-flop 1 and flip-flop 2 has same setup time 90 picosecond, hold time 50 picosecond, and clock to Q is 90 picosecond. For this particular combinational logic, Tmax and Tmin is also given, and these are the clock buffers, and the delay is also given. So in the first part, we are asked to calculate minimum clock period where there is no clock skew or jitter. So let's consider a clock period of T clock, and this T clock should always be greater than T clock to Q of flip-flop 1 plus T combinational max and T setup of flip-flop 2. So here in this equation, we need to consider the worst case delay, because we are trying to calculate minimum clock period. So for the minimum clock period, we need to consider the combination logic maximum delay. So here the clock to Q is for flip-flop 1, and setup time should be flip-flop 2, because sometimes the flip-flop 1 and flip-flop 2 will be having different setup times and clock to Q delays. So in that case, you need to be very careful. So based on the given delays, clock to Q 90 picosecond plus T combinational 700 picosecond plus T setup is 90 picosecond, which is less than T clock. So basically T clock is greater than 880 picosecond. So this is nothing but minimum clock period. Sometimes you will be asked to calculate a maximum clock frequency, that is nothing but 1 by T min, 1 by 880 picosecond. In this case, it is nothing but 1.136 gigahertz. So now we learn how to calculate minimum clock period and maximum clock frequency. We are asked to calculate the minimum clock period when wire delay from clock to flip-flop 1 has longer delay than clock to flip-flop 2. So it is given that T clock to flip-flop 1 wire minus T clock to flip-flop 2 wire is nothing but 90 picosecond. But T skew formula is T clock to flip-flop 2, that is capture flop, minus T clock to flip-flop 1. So in our case, flip-flop 2 is capture and flip-flop 1 is launch. So the clock skew is equal to T buff plus T T wire 1. So this is already given, but here we observe that T clock to flip-flop 1, that is wire 1 minus wire 2, is 90 picosecond. So our skew is equal to minus 90 picosecond, because it is T wire 2 minus T wire 1. So it get reversed. So we got negative skew. So the formula we previously used, right? T clock should be greater than T clock to Q of flip-flop 1 plus T com max plus T setup of flip-flop 2 should be less than T clock. Here we have extra skew, so we should be including it along with T clock, because for the data D1 to reach data D2, there is a skew which is inserted in the circuit, and that skew should account for the clock period. So based on this formula, 90 picosecond plus again 700 picosecond plus setup time is 90 picosecond, which is less than T clock plus skew, that is minus 90 picosecond. So after calculating, this becomes 880 picosecond plus 90 picosecond. That is nothing but T clock should be greater than 970 picosecond. So this is our answer, and this should be minimum clock period in case of negative skew. So yeah, for more examples, please subscribe to our channel VLSI Career Craft, and if you like this video, please like, comment and share. We welcome your suggestions for improving the quality of the solutions. So thank you so much for watching.